Yesterday we talked about the observables and how states and how you set how mathematically you describe the state of the system. In quantum mechanics, we spoke about the we have spoken about the we have spoken about the way we've described it. I've told you that you can either describe the state as some function, but I'll do it in that way. Either as a function, psi, or a vector, or even as a vector containing functions of coordinate and time. We spoke about the scalar product over these states, which is just an integral, or a scalar product of the vectors, or even scalar products of the vector and then integral over the component of the vectors. So I've told you that there can be either discrete or continuous spectrum, which means that measuring some value f, you can your instrument can show you either discrete set of values or continuous set of values. For now, we will speak about continuous. For now, we will speak about discrete spectrum because it is a bit convenient to speak. But everything I'm talking about is can be easily mapped to the continuous spectrum. Yeah, that's where we end up. Okay. The functions in quantum mechanics, usually they are normalized. We've talked about that, but it is not necessary to normalize wave function. But if you have not normalized that, the some equations are changed a little. Okay, as I said, in your state, in the state of there can be some state of the particle can be some state at which there is non-zero probability to measure some quantity, this quantity f, to measure some quantity, to find some quantity f in having values f, having different values. What do I mean? I mean that if you have some particles goes through some instrument f, go through, and it can have value f0, f1, f2, f3, etc. So and here is the probability. Probability equals to some p1. Here's the probability to find the state p3, p4. Before I will continue, you must understand what is probability. What do we mean by probability in this system? We mean that if we prepare a million or billion particles all in this same state psi, and will separately or simultaneously, it doesn't matter. It matters whether they are interacting or not. Let's say separately. If we prepare a billion particles with the same state psi, some part of them, the part which can be calculated as p1 probability times 1 billion goes to the f0 channel, then p2 times 10 to the 9th goes to times billion goes to the f1 channel, and etc. And that how how thing works in quantum mechanics, because I've showed you. Sorry for Tony. I showed you this photograph of the Schrodinger experiment. What is it? It's a photographic plate, and what we see it here is just not trace, but uh, it's a point at the photographic film which was activated by the particle that hit this plate. So it is not some kind of continuous. It's not each particle do not give this continuous nice picture. Each particle gives a dot, but if you put through the instrument a billion or trillion or much larger amount of particles, in physics you usually say 10 to 33 because it's a mole. So, you know, that's Avogadro. Avogadro number is 6.02 times 10 to 23. So it's very, very large numbers, and they form this nice smooth picture. But you should understand that each particle will go either here or here or here or here or even here. But the number of particles here is limits to 0, but it could be either 1 or 2. But here it's billions. Okay. So returning to our measurement, we'll speak about the measurements today a lot. Yeah. So, and this probability, and this, we said that for each eigenvalue, you can address the so-called eigenstate psi1, psi2, psi3. In the meaning that if you put through this instrument the system or particle in the eigenstate psi0, you will definitely, with probability 1, you will get f0 at your instrument. If you put through the instrument the particle in the eigenstate psi2, you will definitely get the particle. Your instrument will show that the particle has the value f2 with probability 1. So every particle in the state psi2 will go to the f2 channel. Okay, but in quantum mechanics, you can build the state shown here, that is constructed from the different possibles eigenstates. And it's called a superposition. So what does it mean? It means that if I put this state psi through the instrument, through our tool, we will get f0 with probability p1 equals to a0, equals to a0 squared. P2 will equal to, f0, I'm sorry, it should be f1, it should be p2, it should be p3. So a1 squared and a2 squared, a3 squared. Before I continue, I should say one more thing. Here, I'm sure that you know, because you all had this mathematical analysis courses, but I should just say that why we are putting this absolute value sign here before taking the square, because in simple mathematics, the mathematical real numbers, a squared will be equal to absolute value of squared. But if we're working in quantum mechanics, we're working with complex numbers, and in complex numbers, if I say if a equals to as the simplest case 2 times imaginary unit I, then you know that a squared equals to 2 times I squared equals to minus 2. So a squared equals to minus 2. But absolute value squared equals to a times a complex conjunct equals to 2I times 2 minus I, because complex conjugations changing the sign of the imaginary unit in the complex number. You know that if a equal b plus ic, then complex conjunct, let's put it here, then complex conjunct a equals to b minus ic. So a times a complex conjunct equals to I times 2 minus I equals to minus 4. Oh, I'm sorry, it's not 2, it's 4 here. Minus 4 times I squared equals to 4. So only the square of absolute value of a is positive, but not the square itself. And the probabilities should be positive values. So we need to take the squares of we need to take the squares of absolute values. So this state is called superposition, and it contains of the set of eigenstates, which with probability an squared, will give us probability equals will give us the value fn. In the direct notations, we can write it in this way. Give me a second. This should be A, not C. Okay. In direct notations, you can write it such way, where this ket vector stands for the eigenstate in the nth stands for nth eigenstates. It's equals to psi n of x. Okay. Another important thing is that every state, no matter what state you will, of the system you will take, can be decomposed in that way. Why is it so? Because no matter what state you will put through the instrument, you will get some numbers. You cannot get no number. You will measure some values of f, and that means that you can how would engineering, practically speaking, just I'm not saying that usual people do that, but how can you do that? How can you decompose that? Can you decompose the state? How can you decompose the state in practical way? You can take billion particles in the state psi, measure the probabilities having these values f0, f1, f2, f3, then say that an equals to square root of pn, and then construct and mathematically construct the state as the sum of an times psi n, where psi n is eigenstate. Here I a little tricked you, because I said that an equals to p1 squared, but Indeed, in this case, squared an will be equal to pn. But here you will in that experiment you wouldn't get information about the so-called phase of the state, because um, of course if I take an equal I times I phi, where phi is some real number, times square root of phi n, the square of absolute number will be still pi n. So in this experiment we cannot get this phase, but still we can get the probabilities. Okay, and this example has the sole purpose of understanding that every state, no matter what state you have, you can decompose by means of the eigenstate of some instrument. It is it is pretty the same as in mathematics. In mathematics, you can you know that almost every so-called good function can be decomposed into the its Fourier series. Let's say f of x, where f of x is function e times minus ikx dx. So every good function, what I mean by good, you know that by good usually mathematician means that it converges at the infinity. This integral should converge at the infinity. So it's quite the same way we decompose the every state, every function of every state into the eigenstates psi n. In the Fourier series, eigenstates corresponds to plane waves e times minus ikx. So if every state can be decomposed in that way, and if putting every state through the instrument will give us some value of n, the sum of these probabilities sum should equal to 1, because I should obtain any of this value f. I cannot obtain no value, and really if I can obtain no value, if there is a possibility to measure no value of observable f, I can name this possibility as f, might say minus 1, and it would be some probability p minus 1, and still now we have a whole set of values. Okay, the sum of these probabilities equals to 1. That means that the sum of the squares of absolute values a n should be equal to 1. So the next question is if we know sorry for jumping. If we know this function psi, and if we know the eigenvalue, eigenfunctions, how can we find these coefficients an? I already told you that you can build an experiments and to measure the probabilities, but still, first of all, it is experimental way, but we want to have a tool for predictions. So we need to have mathematical way of doing that. And another thing that this simple experiment would not give us the phase multiplier. We can show that these coefficients. Oops. Let's go on. I can show that these coefficients is given by that integral. Let's prove it. First of all, we already know that if our state is normalized, the sum of an squared equals to 1, and the integral over the sum normalized state equals to 1 too. So this sum should be equal to this integral. Alexei, sorry. No, it's okay. It was somebody's microphone. I'm sorry.
Да, Тимур.
No, Алексей, все нормально. Я просто подумал, что у вас микрофон включен. Извините. I'm sorry, guys. Yeah. Now we see that this sum equals to this integral because both of these expressions equals to 1. Then let's take this decomposition where yes, we have this decomposition n a n psi n. We can complexly conjunct it. It can be easily done. Then we multiply both sides of this equation by psi, and integrate it. Okay, what would we get? We get the full this. We get maybe I can. No, I can't. We get the following expression. Here I just moved the integral sign into the inside the sum. So integral moved here. Then we can compare. We know that this side equals to n. You see, an conjunct an. But you see that what we have here, compare this sum and this sum. You have this term equal term, and this unknown term, and this known term. This decomposition can be done for any set of an, and if it can be done for any set of an, we can choose as psi and psi complex conjunct. We can choose some function psi m, some eigenfunction psi m. That will mean that this some sign will disappear, and that means that we need to equate this integral to this coefficient. You see that, and that means that an okay, that means that this term behind an complex conjunct and this term behind the an complex conjunct is equal. Psi n conjunct psi dx equals to an, and that is what we wanted to prove. That is. So if we know some some state, if we want to decompose some state into the eigenstates, what we need to do is just to have this scalar product of the given state with eigenstates. Or if we are working in the direct notation, it would be in that way, psi n, psi, that's all. Why I have put psi n as a bra vector? Because you see that psi n here is complexly conjunct, and this scalar product, we remember, is psi n complexly conjunct times psi dx. Note that I here write dx, but actually it can be either integral over one dimensional. It depends on the system. It can be either integral over one dimension, or three-dimensional integral, or two-dimensional integral. So usually they put here q as a general as a variable for general coordinates. So equivalently, I can write here dv, saying that I'm integrating over the whole volume. So note that if you're working in the if you are working not in the with the coordinate function, but as I told you, your state can be can be formalized as some vector a b. This scalar product would be just a simple scalar product. Let's show very trivial way to decompose. Let's say we have a function. Let's say we have function psi1 equal to 1, 0, and psi2 equals to 0, 1, and have some psi equal to a, b. How can we decompose psi through the psi1 and psi2? The first way is very, very simple, because I have taken the simple case. Let's do it another way. Let's take not 1 non. It's too trivial. I take 1 1 and 1 minus 1. So how can we decompose these states? First of all, certainly we can guess. The values behind psi1 and psi2. Here I think it should be I minus b half psi1 plus I plus b half psi ups. I have some borders here. Psi equals to ab equal to, we'll check it, I minus b psi1 plus I minus plus b half psi2. So let's check. A plus b will give a. No, it should be plus here and minus here. But it was only guessing. But how we do it properly, mathematically? We can calculate this this scalar products, because a1 equals to, oh, I'm sorry, that's rather bad. Let's denote it let's denote it as alpha 1. Alpha 1, not A1, but alpha 1. Alpha 1 equals to scalar product of psi 1, psi equals to 1, 1 times A, B, which you know that it is A plus B. And alpha 2, oh, that's one important thing. Here you see that these functions, eigenfunctions I have made, are not normalized because 1 squared plus 1 squared equals to 2. And that's why for normalization I have to put it 1 over square root of 2 here. And in that case we'll have 1 square root of 2 squared plus 1 over square root of 2 squared equals to 1/2 plus 1/2 equals to 1. Okay, so let's put it 1 squared 1 1 AB, and we will have 1 over A plus B. Okay, and alpha 2 is psi 2 psi equals to squared is 1 minus 1 times AB. That equals to 1 squared A minus B. Yeah. So the psi equals to 1 squared A plus B times psi 1 plus 1 squared A minus B times psi 2. If we compare the answer we have guessed and the answer we found, we see that I'm mistaken by the factor by factor 1 square root of 2 because I have forgotten about these normalization factors. So that is how things are usually done in quantum mechanics and how you can decompose the function. You can either guess by if your problem is simple, or you can calculate directly. So another thing is that yeah, let's take this this expression we have proven. Sorry, an equals to integral psi n dq, and then and then decompose psi over all, say psi equals to am psi m. Okay, we will obtain integral psi integral psi sorry, sum am psi m psi n conjunct dq. Then we can transfer the integral into the sum, so change the sequences of summation integration, and we'll get sum over am am integral psi m psi n dq equals to a1 an. But you see that in that sum you already have an. You have an times, let's put it more directly, we have an times psi n dq plus all the sum over m not equal n, an psi m psi n dq equals to an. And we can do that for any set of ans. And that means that if here we have an, here we have an, that means that this integral should be equal to 1. This integral should equal to 1. And this, each of these integrals should equal to 0. And that means that, and here's what I mean, that equal to 1 if n equal to m, n equal to 0 if n does not equal to m. So it means that this scalar product, this integral or function psi m and psi m conjunct should equal to 1 if n equal m, and should equal to 0 if n doesn't equal to m. And that sign, it can be, it is more shortly written by means of Kronecker symbol delta n m, which equals to 1 if its indices are equal, and equals to 0 if its indices are not equal. So that means that the eigenfunctions, eigenstates, eigenfunction that corresponds to eigenstates should be, as they say, orthogonal. That means that that's directly means that the scalar products, psi m psi n equals to psi m equals to 1 if we take the same vector, and equals to 0 if we take the different vector. You should know it. I just repeat a little. It's quite the same principle of orthogonality as we do it in in geometry. Because if we take a vector x, which is 1, 0, and vector y, which is 0, 1, we see that they are orthogonal because 1, 0 times 1, 0, 1 equals to 0 times 1 plus 1 times 0 equals to 0, and 1, 0 times 1, 0 equals to 1 times 1 plus 0 times 0 equals to 0. Let's take our another let's take my another example. These functions, these vectors 1, 1 and 1 minus 1. Let's show that they are orthogonal. Indeed, vector 1, 1 times 1 minus 1 equals to 1 times 1 minus 1 times 1 equals to 0. Because these vectors, it can be easily seen geometrically. Not good. Sorry, it's not very straight line. Yeah, it's not straight. So vector x is this one. It's 1, 0. And this vector is 0, 1, and they are orthogonal. And the vector 1, 1, 1, 1, and this one is 1, 1, and this one is 1, 1, minus 1, and they are orthogonal too, you see. So what we take from this paragraph? We should what you should remember from the paragraph. First of all, the observables, the values, the properties of the particles that can be measured in quantum mechanics, they can have either discrete spectrum or continuous spectrum. Then each state in quantum mechanics, each state of the system particle can be decomposed into the eigenstates, into the eigenstate of the particles. What is eigenstate? Eigenstate is the state at which, with probability 1, eigenstate psi 1, eigenstate psi 1 is the state at which, with probability equal to 1, you can measure the value of your observable Fn. And every state can be decomposed into the some superposition of this eigenstates. These coefficients An give probabilities of measuring the value f having observable f having value Fn. And the last thing, that all these eigenstates, all the set of eigenstates are orthogonal, or as they say, orthonormal, because psi m, psi n dq over the whole volume equals to delta symbol, Schrodinger delta symbol, n m, which equals to 1 if n equals to m, n equals to 0 if n doesn't equal to m. Hey, that's the main concept. Sorry, that's the main concept in quantum mechanics. Next thing is that we still haven't discussed how can we mathematically obtain, calculate these probabilities and these values, how we find the eigenstates. Let's say we have some state and we have some observable f, but how can we how mathematically we find all the spectrum of Fn, and how we find psi n? In that to understand that, we introduce the concept of the average value of the quantity. It's a pretty simple concept. The average value is the average value. It's just the sum of all possible values times the probabilities with which we can find these values. We remember that the probability is just a square of absolute value, the coefficient of decomposition of our state over the eigenstates. So we see that this average value should be bilinear or quadratic in the state in bilinear. You see that it is quadratically depend on the coefficients An. And we know that every states we decompose An psi n, and we want to construct some expression that will give us psi, average f, if we we want the following. We have psi, and we want to construct some expression f that will transfer psi to f to the average f. This expression, you see that here the expression for average is quadratically depends on the coefficient. That means that this expression should quadratically depend on the functions. And that's the first thing we know. And then let us introduce some function, let's say g, some function, let me introduce some function g equal to f psi. I'm introducing an operator which acts to some state f psi and gives function f. And then I say let this operator be so that that the average f is given by this bilinear, this quadratic expression psi conjunct times this g dq equals to psi conjunct f psi dq. Most of you are familiar with the concept of operators, but for some of you that are not, I will say some few words about that. First of all, let's put it here. What is the function? Function of let's take some simple function f of x. It's a real numbered function of one variable. What this function do? It takes x from the real numbers. Actually, it can be not every real number. The function can have only limited domain of operation, and this function transfers some real numbers into another real numbers, and so the function is just a mapping from one one region in the real numbers to another real numbers. So it's just a mapping. So I'm sorry, here not Rn. If we're speaking about single valued function, this function of one variable, it's just a mapping from one number to another. In other words, you can plot the table here x, here f of x. That's our simple functions. And 2, 2, 4, 3, 9, and that will give us f of x equals to x squared. But what is operator? Operator, it transfers some function g, let's say function g of x. Operator f, it transfers to some function h. So it maps some region of functions to some region of another functions, saying that g of x equals to f acting on h of x. Operator can be anything you can think about. The simplest, not simplest, but easiest to understand operator is the derivative. Let's say operator f is the derivative um, of the coordinate x with respect to coordinate x, and acting on the fg gives us dx dg of the x. So acting this operator acting on function g gives us derivative of this function. Another example, the operator can be operator of translation operator. Operator can be defined, translation operator can be defined that way. F of gx equals to gx plus a fa. So it just transfers the function g of x to the function g of x plus a. Okay, that's a few words about operators. So the average in quantum mechanics, if we're given with some state psi, is given by can be found with help of this operator of some physical observable. And let's think about this. The next step is to find the operators, find their properties, and find the operators for each physical quantity. So what about the properties of this operator, and what do they do? Let's look at this expression. F average equals to psi conjunct f times f acting on psi, and let's from the other side, we know that f average equals to fn times an conjunct an. It's the equation that we have, it's this equation. So we have two alternative but equal definition of the average. Either it can be an integral, such integral, or just a sum. Let's use the expression for an in that way and substitute it into this sum. Okay, what would we get? What would we get? We get fn an conjunct an equals to sum over n fn an conjunct an yeah an conjunct sorry yeah and we substitute an conjunct by this equation, psi conjunct times psi n dq. Okay, let's know that I have substituted not an but an conjunct. For an conjunct, we can write down here conjunction, and that's it's just simple. Okay, let's change. Let's do it in such a way. Integral of psi and the sum of n fn an psi n dq. And then we can compare this expression with this expression. I don't know, psi f psi dq. You see that here's psi conjunct, and here's some expression, and here's the f psi. As we can do that for any function psi, we can conclude that this function f operating on psi should equal to this sum. Okay, let's write down it. F psi equals to f equals to sum over n an f psi. I just decomposed the function psi into the eigenstates, eigenfunctions, and then I use this expression sum n fn an times fn times psi n. And now one more time, we can do that for any function, and we can take function psi n for we can take function psi m for which am equal to 1 and an equal to 0 if n do not equal to m. And that means that we can equate acting this function f acting on psi n to the product of fn times f psi n, and that brings us to the following equation, or in direct notation we can write this way, or even we can write in this way: psi n equals to fn. It's f. So that's all three equal notations. They equally can be understood. So what we see here is that psi n is eigenfunction of the operator psi, and fn is eigenvalue of this function. By definition in mathematics, eigenfunction and eigenvalues is the function and values that satisfy this the equation for eigenvalues. Thus, we can say that we see that each physical quantity, each measurable physical quantity, can in quantum mechanics can be associated with a certain linear operator. Some operator, we will speak today about which operator we can associate with which, and the solution and the solutions of the eigenvalue equation, this equation of 4.12, they give us the spectrum of possible values of these possible for measuring values of this observable and it gives us all possible values, spectrum fn, and all possible states psi n, so-called eigenstates. So that is one of the is another major equation of quantum mechanics, the equation of the for eigenvalues in eigenfunctions. You just take the if you want to find out what values what values you can find in experiment, you just take the operator of physical quantity, write down the equation for um, uh, eigenvalue equation, solve it, and find the spectrum of the system and the spectrum of the system uh, and uh, mm, and possible eigenstates. So in the next part, I will speak about the operators or physical quantities that we use in quantum mechanics, and will solve some problems of finding the eigenstates and eigenvalues. So now we have a break, I think 10-minute break. So operators. First, what we should definitely say that if we're choosing operators, there is a principle of correspondence in quantum mechanics. That means that in limit of classical physics, what do we mean by limit of classical physics? It is either very large mass, or very large energy, or very small Planck constant. We just we cannot change it physically, but mathematically in equations we just can find the limit of h limiting to zero. In all these cases, the quantum mechanical laws should transfer to classical laws. That's a principle of correspondence. That's how physical theories are built. Uh, all new theory should, old theories should be a limit of new theories. It's how special relativity works. This in special relativity, if you limit of speed of light to infinity, or no, special relativity, if the velocity of your objects is much less than speed of light, it transferred to classical Newtonian mechanics. And in quantum mechanics, the same. If you work with very large objects, or you mathematically put h to zero, your laws, your equation should transfer to classical one. And you can see it in that way. We already have seen this equation, delta p times delta x, so it's around h bar. So uncertainty in momentum and uncertainty in coordinates is about the Planck constant. And if we work with large, if we limit to h equal to zero, you see that in class, as in classical mechanics, you can arbitrarily, precisely measure the speed, or both speed and coordinate. And even you can see it in another thing. Delta p is delta v, so uncertainty in velocity times mass times delta x h, and delta v times delta x h m. And you see that if m is very large, so h m to infinity, so the delta v times delta x is also tends to be 0. So, and in previous yesterday lecture, we derived the Schrodinger equation for the particle um, particle group, wave packet. And we find, assuming we have decomposing the wave packet into the plane waves, we found that if we act by this operator, where this triangle is a nabla operator, equals to, it's a vector with components y, d, dz. So if we act by this operator by derivative. If we take the derivative of this wave packet, we will obtain the momentum. If we take the first derivative over the time, we obtain the energy. And that our first that is the first operator what where I would speak about is the momentum operator. As I said, the triangle is a noble operator, and we can in components we can write down the expressions for each projection of the momentum into each axis. It is just derivatives. It just derivatives with respect to each coordinate. Another operator we already know is coordinate operator, because in if you're working in real space, if your state psi is given as a function of the some coordinate, so you know that I said that the momentum operator is just derivative up to some constant multiplier tx px, but the coordinate operator is just a multiplication of the wave function by the coordinate. So x is just x. So px acting on psi, px acting on psi equals to minus aih d psi dx. Okay, and x acting on psi is just x times psi. Nothing else. And we already know it, because deriving the Schrodinger equation, I said that the potential function, the potential energy of x multiplying the acting on the wave packet is just a multiplication. So every function of the coordinate, if we say it's operator acting on the function in coordinate space, is just a multiplication of any function on psi. So the next thing, we will we oftenly work with multiplication of the operator. What is multiplication of the operators? Let's take some operator operator f and operator g. Everybody knows what is multiplication of the functions. We just multiply the numbers that gives the function. But multiplication of the operator is a bit more not so. It is intuitive, but not so simple. Let's define the multiplication of. We define the multiplication of operator acting on some function. Not so. Let it be p, not f. So it would be much easier. Acting on some function f coordinate as a sequential operation acting of operator p and g on function f. So operator g, what is the action of the multiplication of the operator? First of all, you need to act by the right hand side operator on the function f of x. You will obtain some function g of x, and then you should act by operator p on the function g of x. In that way, we can find the operator for px times px, which is just square of the momentum. This operator, what is it? It is just, one can think that it is a square of the derivative. No, it is not working that way, because what we, if we are acting on some function, what we have to do, if we're acting on some function, we want to act in that way. Px acting on the result of the acting of function of operator px on function f. Let's expand this expression, just taking the expression for operator minus h minus ih derivative dx acting on minus ih derivative over the x function f. We can just put it here. Minus times minus equals to plus 1. I squared is minus 1, so here we have minus h squared. And sequential derivatives is just derivative of the second order. So it's operator pi p squared is just operator of the second derivative with respect to the coordinate up to this multiplier minus h bar squared. Next operator, what we would speak about, and we will speak about a lot about at the next lecture, is the operator of angular momentum. In classical mechanics, we know that angular momentum is just a vector product. Actually, it's more Russian tradition of notation. In Western notations, you will write, say, Rp in that way, I think, equals to minus h r, yeah, that way. So in classical mechanics, angular momentum is just a vector product of the coordinate vector and momentum. In quantum mechanics, there is we should due to the principle of correspondence, we should say that the angular momentum is also just a vector product of these values. But in quantum mechanics, these values not just real numbers, but operators. And in coordinate space, the r is real numbered function, it's a vector, and the momentum operator is the is just a nominal operator, which as we saw, is just a set of derivatives, partial derivatives. And component-wise, it will be very important for us too. The component-wise, the projections of the angular momentum can be written in that way. It's just a result of the vector product, of these two vectors. Another important example of important operator in quantum mechanics is so-called Hamiltonian operator, which is operator of total energy. From classical physics, we know that the total energy is just sum of kinetic part, p squared. Should not be x here. Give me a second. in classical physics, we know in classical physics, you know that the energy is the sum of the kinetic part, and the potential part. So in quantum mechanics, the total energy is the same sum. Where p squared, we already defined the operator for p squared, and we already defined the operator for potential energy. And in these terms, the Schrodinger equation takes the following form. This form is most famous form because it is most general form of the Schrodinger equation, because Hamiltonian can have not only these simple terms, but it can have in other terms of interaction between the particles, or interaction of particles with magnetic field, all this stuff. But this equation is the Schrodinger non-stationary Schrodinger equation in most general form. So here we discussed three or four operators. First, the basic operator of coordinate, which is thus multiplication of the coordinate of the wave function. Operator of momentum, which is just a set of partial derivatives. Operator of angular momentum, which can be written in that form. And the energy operator, or Hamiltonian operator, which can, in the simple case of single particle moving in some potential, it can be written in the following form. And now I want you to solve some problems. I think I would give you a couple of 5 minutes to solve. Let's begin with problem 4.3. So here is the operator of the projection of momentum on the x-axis. Please find the eigenfunctions and eigenvalues of this operator. And after a couple of 5 minutes, we'll discuss how we do that. We have written the eigenvalue equation. So let's do it in explicit way. So minus h d psi over dx equals to p, which is some number psi. You see that's if you had the course of differential equation, you can immediately solve this equation, or we can just do it in that way. The psi over psi, we can separate the variables, and I p over h dx. We can integrate both parts. It will give us a natural logarithm of psi equals to I p over h bar times x plus some constant, and then exponentially we can write it psi equals to some constant times exponent in pi hx. So what we can say, we see that the eigenfunctions of the momentum operator is the plane waves. It's just these exponents. We can put index p. So if and the eigenvalues is p for that what does it mean? It means that the system with momentum p, with definitely known momentum p, has eigenstate c times e I p h x. So if anybody asks you what is, please write down the wave function of the particle having definite value of momentum, you easily write down. That's very simple. Which is what is a bit more tricky is, let's consider here we didn't consider any boundary conditions. So we consider that our particle lives at the our particle lives our particle lives at infinite at whole space. But let's consider a particle that lives at only at some 0a, at some interval from 0 to a, and before outside that region there is no particle. That means that psi equals to 0, and here psi equals to 0, here psi. Okay, let's find out what is the eigenstates for momentum operator in this system. The give me a second. Can we do that? We cannot do that. Yeah, it seems that okay, we do it a bit later. It seems that you see that we want to solve this equation with the boundary conditions that psi of 0 equals to 0 and psi of a equals to a. Okay, but we have solved this equation, and we have this equation is the first order equation, and that means that we have only one unknown constant, c. We can find this constant from this equation. Okay, psi of 0 equals to c I p over h times 0 equals to c equals to 0. It means that c equals to 0. What does it mean? It means that psi of x equals to 0, that there could not be in that system, you cannot there cannot be a particle with definite value of the momentum that equals to some p. So the solution of this equation gives us information on this system that we cannot put some particles that definitely travels in this interval from left to right, or from right to left. And actually we can understand why is it so, because if we think from the point of view of classical mechanics, what is the possible motions of the particle inside this region? It cannot go infinitely to the right, because there is some wall, and this particle can go through this wall. It cannot go. This particle cannot go to the region with x larger than a, and then in classical mechanics it should bounce and go to the other way, go or other way. And so the motion in classical mechanics, the motion of the particle in that system would be bouncing that way and that way. And we can expect in quantum mechanics that the possible state of the particle in this system would be some superposition of the moving of the particle moving with in that direction, particle moving in that direction. So it's superposition particle having some value of momentum p and some value of momentum minus p. How can we make this superposition? We can make it easily as E C1 E and I P x divided by h plus C2 minus I P x divided by h. That's it. Let's look. I think I will give you this problem as a homework. It depends on what will, or probably will it will be time to solve it today. But now I want to move to another problem. Is that we can show that the angular momentum in the polar coordinates or spherical coordinates, the angular momentum operator can be written down in that way, where phi is the polar angle. I should remind you what is the spherical coordinate system. It's that Cartesian should be x and z, and in the spherical system, in spherical coordinate system, each vector or each point can describe by angle theta and angle phi. The dotted lines depicts this dotted vector depicts the projection of the vector on the xy plane, and that's phi. No, I think that should be x. That should be y. That's the phi angle. The angle between the x-axis and the projection of this vector on the xy plane. So two angles, theta and phi, defines the vector defines the vector in spherical coordinates. Of course, you should add the r coordinate, the distance from the beginning of the coordinate to the end of the vector, so to completely define this vector. So in this spherical or polar coordinates, the angular momentum, the projection of the angular momentum on the z-axis is given by this expression, which phi is the polar angle, which can be equals to which can rotate from 0 to 2 pi. So it can rotate in by 2 pi, and you see 2 pi. The point 2 pi is equivalent to point 0. It means that psi at 0, psi at phi equals to 0 equals to psi at phi equals to pi, obviously, because you just rotated one, just made only one rotation. So please find out the eigenvalues and eigenfunctions of this operator, knowing that the functions the function should depend only on this phi angle. We do not interested in theta, independence of theta and r. So solve this equation. Lz psi of phi equals to some, let's denote it m, psi of phi m. Okay, it should be n. So solve this equation and find all possible values of let me see, I'd say ln. It's always a problem to choose the name for variable ln. Okay, so solve this equation where Lz is, and find possible values of ln and possible functions psi n, knowing that this function should be periodic in phi. I think about 5. After 5 minutes, we can solve it together. You see, let's continue. You see that this operator is the very same operator as momentum operator, and so this equation in explicit form, which can be which can be written in explicit form as minus IH d psi over d phi equals to L n psi of f psi n, and we already know the solution of this equation. Let's do that anyway. We already know the solution of this equation, which is psi n equals to some c times e in I ln over h times phi. So that's the eigenfunctions. Still, it is not the real eigenfunctions because we didn't apply the condition of the periodicity of this function. We stayed because it's angular momentum, because while rotating on 2 pi, you have to be in this at the same point. The psi of 0 equals to psi of 2 pi. Okay, let's solve this equation. Substitute this c times e I ln h bar 0 equals to c times e I ln h 2 pi. Exponent in zeros power equals to 1. We can cut the c, and that means that this exponent equals to 1. What is the solution of the equation IA equals to 1? You know that the solution of this equation is IA equals to 2 pi I, because e in the power of 2 pi I equals to 1. That means that I ln divided by h bar times 2 pi should equal to 2 pi I. 2 pi I. We can, I, and that brings us that ln equals to, oh, sorry, I have forgotten about this n, where n is the natural number, not natural, but give me a second. Where n equals to 0, plus minus 1, plus minus 2, plus minus 2, etc. So it should be n here. That means that ln equal to nh, and that means that psi n equals to c times e in I and h bar h times phi equals to c times e in I and phi. So that is our eigenfunctions, because if and that is our eigenvalues. That means that the angular momentum can have only these discrete possible values. It cannot have any value that let's say h halved or 0.33 times h bar, because in this case the function would not satisfy this boundary or the condition of the periodicity, and only the eigenfunctions that have uh, uh, projections of the angular momentum equal to some number n times h bar satisfy the periodicity conditions and satisfy the eigenvalue equation with these periodicity conditions. And the eigenfunction equals to, they are very simple, some constant times e in power I and phi. So that is how usually how the you saw an example of two possible waves, not two possible waves, but two cases that can be found in quantum mechanics. The first case is when we solved the same equation for the momentum, but we didn't apply it, we haven't applied any any conditions on the wave functions. There was no boundary conditions, and that led us to the continuous spectrum, because the particle in that case could have any value of the momentum, and the value and the wave function could have be any of these exponent depending on the momentum of the particle. But if you apply any limitation of the particle movement, in that case it was the condition on the periodicity of this periodicity of the movement, your spectrum becomes discrete. We've spoken about that in the previous lecture, and we spoke that if the particle movement is limited by some region, and here the particle movement is limited by the circle, because what is the movement? What is the phi going from 0 to pi? It's just a movement on the circle. I'm sorry. Let's do that in that way. It's just a circle. And if particle movement constrained, you obtain this discrete spectrum. The momentum projection of the angular momentum can have only a discrete values, and that is what Stern and Gerlach found in their experiments. Move it here. Oh, we can move it here. As a last The last thing what we want to do here is we can find this constant c. How we can find it? We cannot find it from the eigenvalue equation, because this equation is homogeneous, and you can put any c and any constant you want, but we know that usually we want our function normalized so that uh, psi n squared integral over the whole volume should equal to 1. And our whole volume is limited by just a circle. So our integral is just an integral from 0 to 2 pi over the psi n squared d phi. Let's substitute this one. C times e n phi squared d phi. We know that absolute value of the exponent equals to 1. So integral of absolute value c squared d phi 0 to 2 pi. C do not depend. C does not depend on phi. So that means that we can easily calculate the integral 2 pi equals to 1. That means that c, absolute value of c, equals to 1 over 2 pi squared. And that means that this integral was 2 pi squared times e n phi. Still, we can multiply this function with some face value. Let's say we can put it here, some number a, and this number wouldn't, and this phase factor wouldn't affect any observable or any probabilities. That is why usually people omit it. But it's in some cases, when you consider the superposition of the functions with different phases, it can be important. But in our case, we have only one value. We can omit it and put it just one. So that is the whole solution of our problem. That is how we found the eigenfunctions, eigenstates, and eigenvalues of the angular momentum. We have written down the equation for this angular momentum, eigenvalue equation. We solved it. Then we imposed the boundary or all our other conditions that our wave function should satisfy, and we found that only the values Ln that satisfy this equation, they can be found in experiment. They can be eigenvalues of this operator, and that brought us to eigenvalues and eigenfunctions of this operator. And the last thing that we have done, we normalized our function. We have found the normalization constant. So that's all. That's simple. And the last thing I want to do today is just I have 5-10 minutes. Let's solve a much simpler problem. We know that the projection of Lz on the z-axis Lz have the following eigenfunction. It can be function 0 phi or 1 over 2 pi, 1 over 2 pi plus minus phi, 1 over 2 pi e plus minus 2 phi, and anything you want, any number you want. Let's take the state psi equals to cosine of phi. It is, cosine of phi. It is not a normalized. Actually, we can normalize it, and it would be. Let's take this state and find the probabilities. Probabilities to find the particle, the system having the angular momentum plus h and minus h. So what we need to do that, all we need is, as we remember, just to decompose the psi as a function of an psi n, decompose into the series where psi n is our exponents, and we know that we can find an as the integral of psi n conjunct times psi d phi 0 to p. Actually, and that's how we can find and the probabilities to find angular momentum plus h would be given by the coefficient a plus 1. Probability to find particle with angular momentum minus h would be given by coefficient a minus 1. So all we need to find to calculate this integral. But I will give it you as a homework, and what I want to do now is to do a trick and to solve this problem without solution, without calculating an integral. How can we do that? We know that cosine can be decomposed to the Euler theorem. Euler equation can be decomposed into the following sum. Cosine of phi equals to I phi minus I minus phi divided by 2. Plus. It is plus. So it is 1/2 minus phi plus 1/2. It's I here minus I phi. That's it. We already decomposed. You see that that's using the Euler equation, we decomposed the cosine into the eigenfunctions of the angular momentum operator, because we know that this function, this exponent, is the up to the normalization constant, is the eigenfunction, is eigenstate at which the system has the angular momentum plus h, and this eigenfunction is eigenstate of the system that has angular momentum minus h. That's it. And these coefficients gives us probabilities, but do not hesitate, because you see that if we assume that an equal to a plus 1 equals to 1/2, and a minus 1 equals to 1/2 too, I minus 1 equals to 1/2, then a plus 1 squared plus a minus 1 squared equals 1 half, which equals 1/4 plus 1/4. That means that why we have this, why don't we have explicit 1? We do not have it because we haven't normalized our coefficients. So we have to normalize them. And to do that, we have to divide this each coefficient, properly normalized coefficient plus 1, properly normalized, will be unnormalized divided by square root of a plus 1 squared plus a minus 1 squared. Yeah, that's it. And the same thing for a minus 1. That will bring us to the following. Yeah. So, and if we use this equation, we can find the probability easily. We can easily find the probability p plus 1 is a plus 1 squared divided by the divided by a plus 1 squared plus a minus squared. And so if you have the superposition of unnormalized functions, you can go 2 ways. Either you need to properly normalize your function, or you can calculate the probability without normalizing your function, but in that way you need to divide the square of your absolute value of your coefficient by the sum of square of all possible coefficients. And in our case, it would be square of this coefficient would be 1/4 divided by 1/4 plus 1/4. It would give us 1/4 divided by 1 second. It's 1/2. So without normalizing without properly normalizing the function, we can find the probability to find the system in having the angular momentum plus projection of the angular momentum of z-axis plus h. The probability is 1/2. P equals to 1/2, and minus h, p equals to minus 1/2. So that's all for today. I will give you at a little bit problems, that kind of problem, to get acquainted with decomposition of the states into the eigenstates, and finding and to get acquainted with ways to find the probabilities of the measurement one or another values. So that's all for today. If you have any question, feel free to ask them.